Hello, and welcome to AnalytiXIN Manufacturing Data Assets Research Seminar. This month's seminar is being held by Indiana University, and we have Professors Azad and Lee who will be doing the presentation. So please go ahead and start when you feel ready.
Okay. CR, would you like to say something beforehand, like you said?
I can briefly just give a quick intro here. Can everyone hear me okay?
Yeah.
Cool, fantastic. Just really quickly, very brief intro here today. We'll be hearing from Drs. Ariful Azad and Dr. Wanwei Lee, who are two of our project team members, and they are also members of IU's Intelligent Systems Engineering Department. Ariful is going to kick things off for us this afternoon. Ariful Azad is an assistant professor here in ISE. This afternoon, he'll be discussing the utilization of multiple variables across devices to improve temporal predictive modeling in our ongoing work with energy insights data. So Ariful, whenever you're ready.
Can you see my screen okay?
Yes.
Okay, so let me get started. And we have two presentations. I will discuss our work on multivariate spatiotemporal modeling in the beginning, and then the next speaker will take after that. So I'd like to credit our students, Nicholas Mazeske, Anisha Bajaj, and Shreyash Badia for their wonderful work in this spatiotemporal modeling. So let's see if I can manage that. So in general, many complex systems can be represented as a spatiotemporal system. And when I say spatiotemporal system, I mean that in a spatiotemporal system, we can have multiple entities. In this toy example, we have three entities, A, B, and C. And we often represent those entities as a graph where those three entities will be represented as nodes. And they usually interact with one another through a graph topology, like we have different edges here. And those edges can be directed, meaning that node A in this particular example is influencing node B and C and so on. There are numerous examples like this. For example, a river system where different subbasins, they are influencing one another. In road network, traffic flow prediction, we have a system like this. In our particular example, we have multiple devices like HVACs, and they often influence one another, and we can then capture those dependencies using a graph structure. So that is the special dependency that we can consider in a spatiotemporal system. And then we have temporal dependencies. For example, different entities or sensors, they are generating time series data. And it has many applications in many different spatiotemporal systems. For example, the river network that I mentioned, we have stream flows, and that is usually temporal. In traffic data, we have traffic speed, that is temporal. In our particular application, we have current, power, temperature, they are temporal data. And we can collect those type of data from different devices that are spread across space. So those are spatiotemporal signals that we can get from different devices. In addition to that, in complex systems, we have other features like static feature. For example, location of the system that can be a static feature that is common to all the devices that we can consider. Also, we can have some overall temporal features like season. So that is common for all the time series that we can consider, but that is also temporal because season changes across time. So in a comprehensive spatiotemporal system, we have all those different components that we can consider, and that makes the analysis challenging and interesting. So we are studying this type of system because any energy producing or consuming system has almost all these features. And because of this, we aim to model energy data that we are collecting at different places as a spatiotemporal system. The reason behind this is, again, coming from our data from EMC2. In that data, we can see a clear hierarchy and connection in different time series. So in that data, we see 5 levels of hierarchy. For example, in the root level, we have customer group, OP22, and EMC smart factory. So this is in the layer 1. If we go on level deep, we have the different other devices underneath. If we go even on level deeper, then we have in the layer 3, we have HVAC, energy, and other units. We can go even deeper than that, and we can see we have air handling unit, hot water systems. Even if we go beyond that, then we have in all those devices, we have different measurements coming from sensors like air temperature, supply fan flow, air humidity, and so on. So we see multiple levels of hierarchy in this type of data. And if I represent everything, this is clearly a graph structure that we have drawn in the right side of the figure. And this is a hierarchical structure. The small green dots, they represent one individual time series. And through this graph structure, those time series will interact or influence one another. So that is why this type of data can or should be modeled as a spatiotemporal system, because there is temporal component coming in each of the green dots, and they are connected through this type of graph topology that is defined by the system that we are considering here. So if we talk about data representation, then as I mentioned before, this is clearly a spatiotemporal system where devices and sensors are spread across different buildings in this particular example, or different rooms, and each sensor will emit temporal data. In our data representation, we capture this type of correlation or connection using a graph or network. In some cases, those relationships are explicit. For example, in one HVAC unit, we may have 5 air handling units. So that relationship is quite explicit because one HVAC will contain 5 air handling units. So they should always influence one another. But in some cases, those relationships are not explicit, they can be implicit. For example, how does return fan flow impact return air humidity? Or how does temperature influence return fan flow, something like that. Those relationships are not explicit in the data, but as I will show in our result, that that implicit relationship can help us to predict about the future values. So in our prediction cases, our objective is we target one particular time series, and we aim to predict future values of that time series. For example, we want to predict the future value of return fan flow on HVAC 1. So we in this particular case, we're just predicting one time series in the future. And we're predicting this based on past values of the same time series, past and current values of other time series, other variables in the same HVAC or same device, and also past and current values of other variables, other time series on other HVACs, other units in different parts of the system. So just to repeat what I said, we are predicting future values of a given time series based on past and current values of many other time series that are spread across the system. So there are many ways to predict those type of systems. One simple approach is univariate modeling, where we want to predict future values based on past values of the same time series. This is univariate. We have just one time series. Based on the past data, we can predict future one. That is the simplest approach, and we can simply use traditional recurrent neural networks, LSTM, GRU, those type of things. In the multivariate case, that this is simply extended to predict future values of a given time series based on past and current values of several other time series. So in the multivariate setting, the key question is, do all variables and devices need to be considered for a target variable? Meaning that if we use all the available data in a system to predict something, the prediction may or may not be good, because there will be a lot of noise and some of those things are not relevant for the prediction of a target variable. And also, do all relevant variables contribute equally? For example, if we identify that, okay, the prediction of one variable can be done by prediction of 3 other variables, but still in that case, their contribution may not be equal. So how can we capture that? So in our model, we address this question by applying an attention mechanism with RNN, and that can capture or answer those type of questions automatically from training data. So here is a simple diagram of the model that we are using at this moment. So in this example, X is our input, X is spatial temporal input, meaning that it has both spatial and temporal component. It has multiple variables. In this example, we are talking about F variables. And that means we're talking about F time series coming from multiple devices. And we're also considering T time steps in the past. So if we break this signal down into T time steps, we are noting them in this way. So this, you have T time step signal here. And also, since we have F possible devices or F time series that we are considering, so we are applying some attention mechanism here. So if I have F different time series, so I have F attention scores. Excuse me, sorry. And the sum of the attention score should be 1, and we apply that attention score for each time step that we are considering. So in this horizontal axis, we have temporal attention, and in the vertical axis, we can say, or in each of these cross, we have spatial attention that we are applying for each signal that is coming to our recurrent neural network cell. So the basic framework is a conventional encoder-decoder system where we encode a signal and then we decode it and apply some linear projection to predict future values. But this part is making sure that we can capture only relevant variable and relevant time steps, and also apply some weighting mechanisms so that we can identify or apply appropriate weights to important signals. So this model can capture both spatial and temporal components of energy producer-consumer systems. The temporal part is captured through this horizontal axis, and the spatial components are captured through this vertical axis. It can easily capture multiple variables or multiple devices. For example, in our experiment, I'll show how can we have captured 5 HVAC units available in the EMC2 data. And that can all be combined together in this variable X. And in this case, we are talking about 10 previous time steps, and that all can be captured in this particular model. We have both, and this weighting scheme, these attention scores, they are learnable. We are learning through this data, and that means this step is part of the whole encoder-decoder system. So we always pass the data to the system, and then based on the gradient computation, we can always update the attention scores. So those spatial and temporal attentions, they are actually learnable. So to perform some experiments with this model, we did some data pre-processing. In EMC data, we have total 18 time series in HVAC, but we also have lots of missing data. So for these experiments, we consider 6 variables where we have less than 30% missing data. And we also consider 5 HVAC units for these experiments. Our training testing split is 80-20, which is pretty standard in the literature. And when we predict things, we consider 10 previous time steps, and we use that to predict the next time step. In this particular example, our time step is in minutes, but we can also use different resolutions like seconds, hours, or so on. So here is one particular result. So in this case, we're trying to predict return fan flow. And we have 6 other variables that we are also using. So this is multivariate prediction. The black line represent the ground truth value. And this is the testing data, not in the training data. So the model is already trained and we're trying to predict future values of return fan flow. So the black line represent the ground truth. The red represent vanilla RNN model without any attention score. That means we simply apply recurrent neural network to predict future values. That is also multivariate, meaning that we can also use multiple variables in vanilla RNN. And the green line represent the attention-based RNN, where we apply both spatial and temporal attention. And we can see that in some cases, in the difficult cases, for example, here we have a sudden drop of value. In those cases, the attention-based score performs much better because it is closer to the ground truth values. Similarly, here in this part, we also see that the attention-based model performs better than vanilla RNN or other recurrent neuron models. Here is another example. This is return air humidity. And again, this is multivariate, and it is also across multiple HBAC units. Like in this case, we are talking about 5 units that we are considering. So in some cases, we see that the typical vanilla RNN is performing significantly worse in, for example, here, and also here. On the other hand, the attention-based method that I just discussed, they perform much, much better in those scenarios. And this performance is mostly coming from the use of appropriate variables and setting appropriate weights to those variables. Here is a third example where we are trying to predict mixed air temperature. And in this case, again, we see that in some cases, the attention-based method is performing better, for example, here. In some cases, like here in the blue circle region, the attention-based method is not performing well with respect to the ground truth. And this can happen because of the nature of the attention score. We are investigating those, like when this can, because we are minimizing a loss function for the whole time series. So in some cases, it may perform worse than the vanilla model. But in general, the performance is better than vanilla RNN that does not use attention scores. So if we were to explain why this method, this type of attention score based method is doing better in prediction, here is one particular plot that we can pay attention to. So this plot, let me explain this one. So in the x-axis, in the x-axis, we represent time steps, because in these experiments, we are considering 10 previous time steps. So we have 10 vertical bars represent one time step. In the horizontal axis, we have, in the vertical axis, this one, they represent all the variables that we are considering here. So we have 6 variables and we have 10 time steps. So we have a 6 by 10 matrix. In each cell, we represent the importance of a particular variable at a given time step when we are predicting return fan flow, for example. So here the response variable is return fan flow, and although all of them are input to the system. We can see that we are learning the attention score or weights for different variables at different time steps. And to predict fan flow, we see that temperatures, mixed air temperature and preheat coil temperature, they are more important. The model is learning that these 2 variables are more important when we are predicting return fan flow. And that is why the model is making those variables more important, and that can help us improve the prediction. So meaning that this type of unequal weighting scheme, where more important variables are getting more weights, can help us improve the result, and that can be reflected in our prediction values. For example, here we see that attention-based RNN is performing better than regular RNN. However, this is not surprising because fan flow, whenever if fan flow is determined by something, it should be by temperature. So from physics point of view, it perfectly makes sense. However, this model is learning this automatically because we have not input this type of information to the system. The model learns this reasonable dependency automatically without any knowledge about physics. And that is one way to validate this type of approach, saying that if it can identify important variables automatically, and that is backed by our knowledge about physics, then that is perfect. That means it can identify all those dependencies automatically without user input. But physics-informed model should perform even better if we can actually put those information directly into the model in the beginning. And we're investigating that. If we can actually put those information, some human learned information directly into the model to improve the prediction even further. In some cases, we observed that none of the other variables are significantly important. For example, whenever we try to predict mixed air humidity, we only observe that only mixed air humidity is important whenever we're predicting mixed air humidity. That means past values of mixed air humidity is influencing the future values of that particular variable. Other variables are not that important. We have not, this model is identifying this automatically. So if it recognizes that other variables are not very helpful for future prediction, then it can simply ignore them. And that will be done automatically from training data. We don't have to do anything to make this happen. So that is our current status. We are doing multivariate predictions based on attention-based recurrent neural network. As for the future work, we are trying to incorporate the dynamics of the system using knowledge graphs. A knowledge graph is a graph structure where we can actually store entities and relationships, and they can change dynamically over time. So that is our next step. We will model everything using a dynamic knowledge graph. And we also using this, so the result that I have shown is from EMC2 data, but we now have data from our own sensors from IU, and we also have access to other industry data sets. So we are actually applying this model for those type of data sets and see if the prediction is better or by how much. And also we are incorporating this into our real-time forecasting system, and it will be available on the dashboard that Pratik discussed in one of the previous meetings. So that's all from my side. Thank you. Please feel free to ask me questions.
Thanks, Ariful. Unless anyone's got anything immediate that they want to pose right now, we may wait to hold questions until the end. So with that in mind, whenever you want to pass that control over to Wanwei, that would be great. Now we'll go ahead and introduce our second presenter. Wanwei Li is a postdoctoral fellow working with Dr. Vikram Jadhav in ISE. His presentation this afternoon is going to focus on the usage of Prophet to predict energy consumption and the usage of unsupervised learning in project data analysis. Wanwei, whenever you are ready, take it away.
Okay, thanks for the kind introduction. Can you see my screen right now?
Yes.
Okay, thanks. Okay, good afternoon, everyone. My name is Wanwei Li, and I'm a postdoc in Vikram's group at Indiana University. So today I'm gonna talk about some preliminary results of predicting the time series data by Prophet. Yeah, predicting, there are different ways to predict the time series data. For example, just a couple minutes ago, Professor Arif Azad used the univariate and the multivariate LSTM or RN model to predict the temperature and the humidity and etc. And also we have heard that from Professor Minchu's group in Purdue University, they use artificial neural network and support vector machine models to predict the time series data. This machine learning based method are flexible but need a long time to train. And also there is non-machine learning based method. We also heard from our previous seminar in Professor Minchu's group, and they performed the building thermal model. And this kind of method is easy and fast to apply, but less flexible. So today I will examine another non-machine learning based method, which is called Profit. This is a package developed by Facebook and can be implemented in R and Python. It's fast and provide completely automated forecast that can be tuned by hand. Okay, let's dig into the Profit. Profit is a procedure for forecasting time series data based on the attitude model, where the nonlinear trend of it with yearly, weekly, and daily seasonality, and plus holiday effect. It works best with time series that has strong seasonal effect in several seasons of historical data. And the Profit is robust to missing data and shift in the trend, and typically handles outliers well. And for example, this is a good example for the Profit to feed and predict. This is a number of events on Facebook from 2013 to 2016. You can see at the end of each year there is a dip for the data, and also in the middle of the year it also has dip in each year. So for how the Profit works, it is a decomposable it's a decomposable time series model. It includes a trend, the seasonality, and holidays. So it's also enabled to include new components to this model, to this equation. And this epsilon t is that represent those model is not something is not accommodated by the models. Assume this epsilon t is normally distributed. So for the trend function, it represents non-periodic change in the value of the time series, and has two different equations or the growth model. The first one is the logistic growth model. C is the maximum capacity, but in Profit it can be treated as C is time dependent, and also it can set different time steps, and you can set on which time step the increase rate can changes. A actually is a piecewise function, either 1 or 0. So here, and another model for describe the trend function is the piecewise linear model. So this is how the Profit to describe the trend. And for the second component is the periodic change. It uses cosine sine functions to represent the periodicity of the data. And then n is determines the change in frequency. So this number also can be manually changed. One thing to be noted that if you use a larger n, that this probably can cause overfit. And P is the periodic time here. And AN and BN are the fitting parameters. And finally is the holiday effect. That's represents some irregular schedules over one or more days. So, so in profit, we can build our own calendar to explicitly say which days are holidays, and it also can it also has in default calendar is based on different countries. So for example, we can add a customized holiday, for example, Super Bowl in the calendar, and the profit can automatically check whether this day is in the holiday list, and if it is in the holiday list, and they will add this function to this component. If not, this term will be canceled. Okay. And finally, this is how the profit feed the data for Facebook event and give its prediction in the next half of the 2016. So before we examine how the performance of profit on the net energy data, we first look briefly introduce the data itself. So there are three sensors installed in FAMES lab at IU to measure the energy usage. And each sensor has three phases, phase A, B, and C. And those sensors are monitoring multiple devices such as pulsers, jaw towers, oven, rheometer, muffle, and firebox, glass lathe, etc. For example, in this figure here, it has higher energy uses than the neighbor point. That means there are some devices running in this time period. Okay, so first, let's look at how profit works on. I just give like 30 days for the input data for profit, and let the profit feed the data and give a prediction in the next 3 days. Yeah, the data is hourly based. So I can see one point for the profit is it treat this higher point as the outliers. But this actually is some devices running in this time period, and leads to a higher energy usage. And this is important for energy hour prediction actually, but it doesn't capture it by, or it omitted by profit. And the profit also can give a daily and weekly periodicity, how the energy usage. For example, we can look at the daily one. So from 8 a.m. to the 8 p.m., the energy usage is higher than the rest of the time. This is expected. The next is I put all the available data as the input to feed the model. It's from mid of the January to the end of May, and let profit to feed them data and give a prediction of the next 3 days. This is for the M00 sensor in phase A. And also this is the same sensor, but for phase B. And this for phase C. Phase C. And let's look at how the prediction works, the performance. So the blue line is the prediction from profit, and the orange line is the ground truth in the 3 days. You can see there is a higher peak for the ground truth. That means some devices were running in this period, but the profit doesn't capture this data. So this is the good thing for profit is it's very fast. It only takes like several seconds to finish the feeding and give the prediction. But the drawback for the profit is that it doesn't capture some outliers. But the profit treated as outliers, but it's important for our energy for the prediction. So my idea for this for fixing these outliers is that we can treat these outliers as a holiday effect. We can input this time period as a holiday to mimic the abnormal changes from the ground from the basic state. So this is the preliminary results for the profit prediction. And thank you for your attention, and I'm open to questions.
Thanks, Marie. Yeah, at this point, if folks have any questions that they'd like to jump in with, either for Dr. Assad or Dr. Lee, that would be fantastic. If you don't mind mentioning your name and then mentioning which person the question is for, and then proceeding with your question, that would be super helpful.
Yeah, can I ask a question? This is for Professor Azad.
Yeah, sure.
Yes, sure, please.
If it is possible to share your screen, that would be great. Thank you.
Okay.
All right. In terms of in slide 8, I just have some clarification question. I'm new to this, so. So is the X variable, is it X essentially a matrix that you have not only the T time points, but also if there are F, so is it a T by F matrix, that X?
Yes.
All right. And A naught is just a vector. So your X, every X is when you X tau over minus T or tau, that one is really a vector that you're multiplying with A naught. Is that right?
Yeah, so you're right, yes. So X is a matrix, and here each component is one time step here.
Nice.
Which is a vector, yes.
Yeah. So the two things I did not understand, that in one case you had the 6 variables and all the weights were really close to 0.16. I think if you go down a slide or two, and 0.16 versus 0.17, it looks like all the variables were equally important. And I don't understand from a physics side how it can be equally important. So if can you go down to the 1 or 2 slides down?
Yes, okay. So yeah, actually, that is a very nice point. Actually, we are discussing about that internally. And this has something to do with our loss function and our softmax layer that we are applying in the end. So we are trying to fix this. And I think we want to make sure that they are as extreme as possible. And I am hoping that we can control this to some L1 regularization so that we can specify things. Things are not
Nice.
important, should be 0. Things are important, should be close to 1.
Right. The
So
other
this is
one is
happening-
I'm sorry, go ahead.
So this is happening automatically in the softmax layer that we are applying in the end. But actually, we are aware of this problem, and we are trying to fixing this because it is hurting our interpretability.
Right. And didn't you say that there are 3 or 4 HVACs that are you are doing it simultaneously? So is the other HVACs not, this is the self variables, right? For let's say HVAC 1, you have this. HVAC 2 had a set of parameters also. HVAC 3 has a parameter. Does HVACs have any crosstalk? Or you are just doing it for your own HVAC and not bringing in the other HVACs variables?
These are from all HVACs. Nick, you are here. Are you here?
Yes, sorry, I was muted.
Can you confirm that these variables are they from all HVACs in this figure?
Yes, there is one attention matrix as you're seeing here, and it is fitted. Well, it depends. We considered several scenarios, but I believe this one is from the multi-device scenario. So that would be all 5.
But this is what I'm trying to understand, that all these boxes have the same color. And that would mean, each box has the same color. That means that neighboring HVACs have equal importance to, the cross importance is the same. And how can that be?
Yes.
That the cross importance is the same? Because, they don't know about each other. They are externally correlated because external temperature is probably the similar, but how can they be equally important? That was not clear to me.
Yes, they could be. There certainly can be a difference in importance from device to device. And one thing we did to, kind of make sure that these learned importance scores, at least the relative values of them, checked out with some kind of evidence, was to compute the correlation between all of the variables for each device separately. And that was something that I actually looked at to confirm, was to kind of see how the correlation was different from device to device. And they're actually very consistent. They might be off in the first or second decimal place, but never in the, they might be off in the second or third decimal place, but never in the first. So they are very, very close. And I believe what you're getting at is that we should probably have a separate matrix, attention matrix for each device. Is that correct?
Yeah, I'm just wondering, I'm just thinking about physics of the problem. Mm-hmm. And just thinking that how should I ask the machine or this machine learning algorithm, how should I set it up so that I don't overload it with too much information? So
yeah. Well, to completely model it, we would want, one attention matrix for each device, because, potentially the correlations between variables, between, signals could be specific to each device. They could be different significantly. That's not something we saw, and we chose to stick with one matrix for, to try and avoid overfitting, because I think that would be a more complete model, is a one attention matrix for each device, but that started to become a pretty significant number of parameters and potentially overfitting.
Thank you. This is very nice work. Maybe we can set up a time when we can discuss this. I'm very interested in understanding whether we can get some insights out of this. So thank you.
Okay,
sounds great. Thank you.
I think in the long run, what we are planning to do is to develop a hierarchical model. There is a clear hierarchy. So this is the data, and we can see hierarchy. So if I have 2 HVAC units, they form a hierarchy and they're part of one bigger units. So currently we are collapsing all the HVACs data together to represent one attention score for one variable, but there is a clear hierarchy, and this should be a hierarchical model if we have enough data. And that is the direction that we are going into.
Thank you.
Thank you.
Still got a good amount of time here left for discussion. Are there any other questions?
Well, if there are no more questions, thanks everyone for attending the seminar, and we will post the recording and send the link to everyone shortly.
Okay, thank you.
Thank you.
Thanks, folks. Have a great afternoon.